Section 1. The Cosmic Background. The universe's natural temperature. Imagine drifting through the deepest void between galaxies. There are no stars here, no light to guide you, no warmth to touch your skin. The Milky Way itself is only a faint, silvery arc in the far distance. All around you is silence, the truest silence in existence. And yet, even here, in the loneliest part of space, something invisible hums faintly through every atom of your being. It is the afterglow of creation, the cosmic microwave background, the quiet light left behind from when the universe itself was born. Everywhere you go in the cosmos, this light follows. It fills all of space, stretching endlessly in every direction, bathing the entire universe in a uniform, invisible warmth. It is not much, only 2.725 Kelvin, just a few degrees above absolute zero, but it is the baseline temperature of everything that exists in the vast cosmic void. To understand how the universe became so cold, we must travel backward, not through space, but through time. Over 13 billion years ago, everything was heat. The newborn universe was dense and radiant, a storm of light and plasma, where matter and energy were tangled together in a blinding, churning sea. Temperatures soared above 10 billion degrees, and the smallest particles moved faster than imagination could grasp. But as the universe expanded, it cooled. The light stretched, its wavelengths growing longer, softer, dimmer. What began as white-hot radiation became the faint microwave glow that now surrounds us. This cooling never stopped. Space itself continues to stretch, carrying galaxies farther apart and lowering the energy of the background radiation, little by little, century by century. The cosmos, once a furnace, is now a near-frozen ocean of emptiness, its temperature locked at a level that only the most sensitive instruments can even detect. In the 1960s, two engineers, Arno Penzias and Robert Wilson, stumbled upon this ancient glow by accident. Working with a radio antenna in New Jersey, they found a strange, persistent hiss in their data. No matter which direction they pointed the antenna, the noise was there. At first, they thought it might be due to interference, or even nesting pigeons inside the dish. But after cleaning, testing, and retesting, the signal remained. What they had discovered was nothing less than the echo of the Big Bang, a relic of the time when the universe became transparent, about 380,000 years after its birth. That faint radiation is now one of the most precious maps in cosmology. When we look at the cosmic microwave background, CMB, we see not just temperature, we see the first ripples of matter that would one day form stars, galaxies, and worlds. Every patch of it tells a story. Some regions are infinitesimally warmer, others slightly cooler, differences of millionths of a degree. But these tiny fluctuations are the fingerprints of structure, the seeds from which everything we see today eventually grew. And yet, what truly humbles the mind is its sheer stillness. A temperature of 2.7 Kelvin means that, on average, Every atom in space vibrates with almost no motion. It is a realm of quiet energy, a soft, cosmic twilight that never ends. If you could float there, you would not feel cold in the way we understand it. You would not shiver or freeze, because there is no air, no medium to carry the chill. You would simply drift in the slow heartbeat of the universe itself, bathed in a light that has traveled for over 13 billion years to touch you. The CMB is a reminder that temperature is a story of time. As space expands, wavelengths stretch, and the universe cools. If expansion continues forever, then so too will the cooling. The cosmic background will fade ever closer to absolute zero. In trillions upon trillions of years, the last stars will burn out, galaxies will dim, and the background will be so cold that even the most delicate radiation will carry almost no energy. The universe, once a firestorm, will become a silent, frozen sea, a state cosmologists call the heat death or the big freeze. In this distant future, the cosmic background will still exist, but it will be unimaginably faint, stretched into wavelengths longer than any human instrument could ever detect. The universe's temperature will hover just above absolute zero, a few trillionths of a Kelvin. Even then, the faint whisper of the Big Bang will remain, like an eternal breath, frozen in time. To stand under that ancient light, or even to think of it, is to feel the scale of time itself. Every second you live, every breath you take, happens within this invisible ocean of cold radiation. It surrounds you now, passing through your body as you read these words. Billions of photons, born from the dawn of everything, flow through you every moment, unnoticed and gentle. They carry the memory of beginnings. When astronomers map the CMB, they are not just charting temperature. They are tracing the fading warmth of creation, the cooling of a once fiery cosmos into calmness. Each photon in that radiation began its journey when the universe was young, when matter first formed, and light could finally travel freely through space. Now, after billions of years of expansion, that same light has lost nearly all its energy, stretched into the microwave band. But it has never stopped moving. It continues its silent flight through infinity, painting the universe with a uniform, delicate chill. There is beauty in that constancy, in knowing that every galaxy, every planet, every creature lives within this faint warmth that connects us to the origin of all things. It is as if the cosmos still breathes, slowly, softly, cooling itself as it drifts through time. And yet, even here, in the most uniform cold we can imagine, there is motion, there is life, there is memory. The universe cannot reach absolute zero. It cannot stop entirely. There will always be that faint hum, the leftover energy of existence itself. The cosmic microwave background, then, is not merely a temperature. It is a reminder of balance between fire and silence, between creation and stillness, between what was and what remains. When you look up at the night sky, the starlight you see is young by comparison. The true light that fills the universe is invisible, ancient, and cold. a blanket woven from the first heartbeat of the cosmos. In its chill, there is peace. In its silence, there is story. And in its endless persistence, there is the promise that even as the universe grows old and quiet, it still carries the warmth of its own beginning. Section 2. The Dark Nebulae, where light hides and cold deepens. Far beyond the glow of any star, where light fades into obscurity and color gives way to velvet black, there exist immense clouds of gas and dust that quietly drift through the Milky Way. They are called dark nebulae, regions so dense, so cold, that they swallow starlight whole. To the human eye, they appear as silhouettes, shadowy patches against the bright canvas of the galaxy. Yet inside them, something extraordinary happens. They are the cradles of creation, and paradoxically, some of the coldest places in the universe. Here in these invisible sanctuaries, the temperature can fall to as low as 10 Kelvin, only 10 degrees above absolute zero. At such frigid depths, atoms move sluggishly and molecules form that would disintegrate in warmer realms. The simplest elements, hydrogen, helium, carbon, oxygen, begin to combine into icy molecules like water vapor, ammonia, methane, and even organic compounds that are the precursors to life. It is within these dark, frozen clouds that the universe begins to dream of stars. When we look up at the Milky Way on a clear night, we often see lanes of darkness weaving through the bright starlit band. To ancient observers, these voids were mysteries, gaps in the sky, places where heaven seemed to falter. But they are not gaps at all. They are nurseries, veiled by their own richness. The dust within them is so thick that visible light cannot pass through. Only the longest radio and infrared waves can penetrate the gloom. Inside, shielded from radiation and warmth, molecules gather and cool. The gas is so sparse that a cubic centimeter might contain only a few hundred atoms, far emptier than any vacuum we can create on Earth. Yet across light years of distance, this rarefied matter adds up, forming vast blankets of cold dust stretching across interstellar space. In this frozen environment, heat is a precious rarity. The only warmth that exists comes from the faint glow of nearby starlight or the gentle pressure of cosmic rays. Even then, it is not enough to stir much motion. Everything within the cloud moves slowly, delicately, almost like a breath that has forgotten how to rise. But cold is never lifeless. Deep inside these nebulae, the cold serves a purpose. As molecules lose energy and slow down, gravity begins its patient work. It draws the densest regions inward, pulling matter into invisible knots. Over millions of years, these knots compress and heat, their centers growing warmer as gravity tightens its embrace. Eventually, if the balance holds, the cold gives birth to fire. A new star ignites, glowing against the darkness that nurtured it. This contrast between the frigid emptiness of the nebula and the blazing heart of a newborn star is one of the most poetic cycles in nature. From cold stillness comes light. One of the most famous of these frozen realms is the Boomerang Nebula, about 5,000 light-years away in the constellation Centaurus. Astronomers call it the coldest known natural place in the universe. Its temperature is measured at just 1 Kelvin, colder even than the cosmic microwave background. The Boomerang Nebula is not a dark nebula in the traditional sense. Rather, it is a cloud of gas ejected from a dying star. But its existence reveals just how profoundly the cosmos can cool itself. As the gas expands rapidly into space, it loses heat through adiabatic cooling, the same way air cools when it rises and expands in Earth's atmosphere. The result is a region of space so cold that it outchills the very universe itself. Yet, within dark nebulae, the same physics applies on a gentler scale. The balance between compression and cooling determines their fate. If gravity wins, stars are born. If pressure or turbulence holds them apart, they remain eternally dark, quiet archives of cosmic potential. Inside them, the chemistry of cold unfolds in strange and subtle ways. At temperatures near 10 Kelvin, molecules stick to dust grains, forming icy mantles. Carbon, oxygen, and nitrogen atoms combine into complex organic molecules that cling to these frozen surfaces. These compounds, amino acids, alcohols, and hydrocarbons, are the seeds of biochemistry, preserved in the dark for eons. When new stars eventually ignite and warm their surroundings, these ices vaporize, releasing the building blocks of life back into space. Some of that material will later form planets, oceans, and perhaps creatures capable of wondering about where it all began. So the dark nebulae are not just cold, they are creative cold, fertile silence. To observe them, astronomers must look not with eyes, but with instruments that see in infrared and radio wavelengths. Through these, the dark clouds reveal their hidden structures, vast tendrils of dust, twisting through space, dotted with denser clumps where new stars are forming. In these images, one can see the architecture of stillness itself. Filaments and voids sculpted by magnetic fields and gravity, shaped by cosmic winds. They look like frozen rivers, flowing slowly through the night of the galaxy. Each dark nebula tells a story of patience. Stars are impatient compared to these clouds. They burn and die within billions of years. But nebulae can drift in quiet equilibrium for much longer, changing only subtly with the ages. If one could float within such a nebula, the view would be surreal. An infinite twilight filled with soft, scattered glows from distant stars, barely visible through the dust. Around you, microscopic grains of frozen carbon and water drift like snowflakes, reflecting the faintest light. It would be utterly still, utterly silent. You could stretch out your hand and touch nothing, and yet touch the birthplace of everything. The cold here does not destroy. It preserves. It waits. To understand these dark nebulae is to understand the quiet side of creation, the stage before the lights rise. They remind us that every bright thing in the universe begins in darkness and cold, nurtured by silence until the moment of ignition. The warmth of your body, the fire of our sun, the glow of every distant star, all of it owes its existence to these quiet, frigid nurseries. The cold was never an absence of life. It was the pause before the beginning. And so, when we speak of the coldest places in the cosmos, we are not only speaking of stillness, we are speaking of origin, of the dark chambers where the universe gathers its breath before whispering stars into being. In those shadows, light is only sleeping. Section 3. The cold hearts of dying stars, when fire becomes ice. Every star that shines is a furnace. For millions or billions of years, it burns with steady devotion, transforming hydrogen into helium, light into warmth, time into memory. The energy that spills from its heart travels across the vastness of space, touching worlds, stirring oceans, and giving birth to life. But no fire lasts forever. Eventually, every star exhausts its fuel, and when the final reactions cease, when fusion itself grows still, the same star that once lit the heavens begins to cool. What follows is a slow, cosmic exhalation, a transition from fire to silence, from light to cold. When a star like our sun nears the end of its life, it grows swollen and red, expanding into what astronomers call a red giant. Its outer layers drift away, carried by solar winds that form soft, glowing shells of gas. At the center, the star's core, the heart of all that light, shrinks and contracts under its own gravity. Without fusion to support it, the star can no longer resist collapse. The immense pressure compresses its matter tighter and tighter until the atoms themselves buckle. What remains is a white dwarf, a stellar ember, small as Earth, yet holding the mass of a sun. For a time, it glows faintly, its light no longer fueled by fusion, but by the residual heat trapped inside. It shines with the soft, fading glow of a dying fire. White dwarfs begin their afterlife scorching hot, with surface temperatures exceeding 100,000 Kelvin, but they have no source of new energy. So, over billions of years they cool, radiating their last warmth into the void. As millennia pass, they fade from white to yellow, then to red, and eventually to black. A black dwarf, a star so cold that it emits no light at all. None exist yet. The universe is still too young. Not enough time has passed since the first stars were born for any white dwarf to have fully cooled. But in the far future, long after the galaxies have dimmed, the cosmos will be filled with them. Frozen stars, quiet and dark, like the stones of a once blazing temple. In these black dwarfs, matter will exist in one of its most silent states. Atoms are packed so closely that they behave more like a crystal than gas. Temperatures will hover just above absolute zero, and time will seem to have no meaning. These are the cold hearts of dying stars, not lifeless, but timeless, existing in an eternal pause between energy and stillness. Some stars, though, end not as gentle embers, but as violent collapses. Massive stars, those many times larger than the sun, live fast and die young. When they run out of fuel, they don't quietly fade. They explode in cataclysmic supernova, scattering their outer layers into the galaxy and leaving behind cores of unimaginable density. If the remaining mass is small enough, it becomes a neutron star, a sphere only about 20 kilometers across, but heavier than the sun. Its matter is crushed so tightly that protons and electrons merge into neutrons, forming a single, giant atomic nucleus held together by gravity itself. At birth, a neutron star can reach temperatures of 1,000,000 Kelvin or more, but it cools astonishingly fast. Within a few million years, the heat dissipates into space, and the surface temperature drops to a few 100,000 Kelvin. Still far hotter than any fire on Earth, but frigid compared to the inferno it once was. Inside, the story is stranger still. Deep within the core of a neutron star, the density becomes so extreme that even neutrons begin to dissolve into a soup of subatomic particles, quarks and gluons. The matter here may exist as superfluid, a phase that flows without friction, behaving more like a wave than a solid. It is possible that, as these exotic fluids cool, they form superconducting crystals that trap magnetic fields for eternity. In the depths of the coldest neutron stars, the universe reaches temperatures of mere tens of thousands of Kelvin, a frozen quantum landscape at the heart of what was once a living sun. And beyond even these remnants lies the ultimate stillness, the black hole. When a massive star collapses entirely under its gravity, it leaves behind a singularity, a point so dense that space and time themselves fall inward. The temperature outside a black hole, in the empty vacuum of its event horizon, is theoretically absolute zero. No heat escapes, no light, no sound. Yet, paradoxically, according to quantum physics, black holes are not entirely cold. They emit faint Hawking radiation, a ghostly whisper of energy leaking from the edges of the event horizon. For the smallest black holes, this radiation could be warm enough to be detectable. For the largest, it is unimaginably faint, a temperature of 10 to the minus 8th Kelvin, barely above nothingness. It is here, in the edge between gravity and emptiness, that the cosmos brushes closest to true absolute zero. When we think of stars, we imagine fire, brilliance, warmth. But every fire casts a shadow, and the shadow of a star is its frozen heart. As time passes, the galaxy grows dimmer. One by one, the stars will fade into white dwarfs, neutron stars, and black holes. Eventually, trillions of years from now, the last white dwarf will cool into darkness. The last neutron star will grow silent. Even the black holes will evaporate, releasing their final particles as faint bursts of radiation before disappearing into nothing. The universe, in that far future, will be a place of near perfect cold. Only the faintest glimmers of energy will ripple through the void, remnants of what once was, the final, slow exhalation of cosmic heat. And yet there is a quiet beauty in that destiny. The cooling of stars is not an ending, but a transformation. It is the return of energy to stillness, of creation to silence. Every photon a star ever released continues to wander through space, carrying its warmth forever forward. Even when the star itself becomes ice, its light still travels, still touches the edges of eternity. In the end, the universe's cold hearts are not symbols of death, but of endurance. They remind us that all things, even suns, find peace in stillness. The fire that once burned does not vanish. It only changes form, becoming memory, becoming calm. When you look up at the night sky, you are not only seeing living stars, you are seeing ghosts, remnants of fires long extinguished, their light still crossing space to reach your eyes, each one a story of warmth, fading into infinite quiet. And perhaps, somewhere in that quiet, the universe is simply resting, preparing as it always does, for whatever new dawn will one day follow the cold. Section 4. The temperature of nothing. How cold is the cosmic void? Close your eyes for a moment. and imagine the purest emptiness you can conceive. No wind, no dust, no breath of light, just the silent expanse that stretches between galaxies, so wide that even starlight seems to lose its way. We like to call it the void, but the word nothing is misleading. Space, even when stripped of matter, is not truly empty. It trembles, it hums, it carries a temperature, one so faint, so close to nothing, that it challenges the very definition of what cold means. At first glance, you might think emptiness should be absolute zero. After all, temperature is motion, and in a vacuum, there is almost nothing to move. Yet the universe resists such perfection. The void still glows faintly with the remnant warmth of the cosmic microwave background, that 2.7 Kelvin radiation that lingers from the Big Bang. Wherever you go, those ancient photons pass through you, giving the universe its natural baseline. But the deeper truth lies below that faint glow. Even if you could somehow block every photon, shield yourself from every star, and silence all radiation, the temperature of space could never truly reach zero, because quantum physics forbids perfect stillness. Within the emptiness of a vacuum, tiny fields fluctuate endlessly. Particles appear and vanish. Pairs of opposites, matter and antimatter, blinking in and out of existence in time shorter than an instant. This restless sea of quantum foam ensures that the void is never completely at rest. There is always a whisper of energy called the zero-point energy. This zero-point energy gives the vacuum a temperature that cannot be erased, a fundamental trembling that persists even when everything else has gone still. It is as though the universe itself refuses silence, insisting on keeping a soft, eternal breath. Physicists have learned to measure this delicate hum indirectly. When they cool atoms in laboratories to near absolute zero, the atoms stop moving, but they still jitter faintly, proof that quantum motion can never be fully frozen. The same principle holds true across the cosmos. Emptiness, too, vibrates with possibility. The temperature of the void, then, depends on what you consider nothing. Between stars inside a galaxy, stray particles of gas warm space slightly, to about 100 Kelvin in some regions, or a few tens of Kelvin in others. Step beyond the galactic outskirts into the intergalactic medium, and the temperature drops sharply. There, only a handful of atoms drift through a cubic meter, and their random motion corresponds to just a few degrees above the cosmic background. Farther out still, between the great filaments of the cosmic web, lie the true voids, regions hundreds of millions of light-years across, where there is almost nothing at all. These places are colder still, so cold that their background radiation is nearly the only measurable energy. They are deserts of near-perfect stillness, where the temperature rests infinitesimally above the universal minimum, 2.7 Kelvin, decreasing slowly as the cosmos expands. If the universe continues its expansion forever, these voids will grow colder with time. The cosmic background will stretch to longer and longer wavelengths, its temperature halving, then halving again. In perhaps 100 billion years, the temperature of the universe will be less than a single degree above absolute zero. And in the farthest future imaginable, the radiation will fade until its warmth is almost imaginary, a mathematical whisper hovering above nothingness. To speak of the temperature of nothing is to face the limits of both science and language. Temperature, by definition, describes the collective motion of many particles. But when there are almost no particles, when the density approaches zero, the very concept becomes ambiguous. Does it make sense to speak of heat where there is nothing to be heated? The answer depends on scale. In small regions, we can talk about the temperature of radiation, the average energy of photons that pass through. In larger volumes, we speak instead of entropy, the measure of how evenly that faint energy is spread. The cosmic void has incredibly low entropy compared with the early universe, yet paradoxically, it represents the end state of cosmic cooling, the universe's inevitable slide toward equilibrium, where every place becomes as cold and featureless as every other. In that distant destiny, temperature loses its meaning because differences vanish. Nothing is warmer or cooler. Everything simply is. And yet, even now, the void is not perfectly uniform. Here and there, small eddies of structure remain. Lonely galaxies, drifting clusters, the faint hiss of ancient quasars. Their light still travels through the emptiness, raising local temperatures by the tiniest fraction. Occasionally, energetic particles from cosmic rays streak across the vacuum, momentarily stirring its quiet. These flickers remind us that the universe, though cold, is not dead. The emptiness between things is part of the rhythm of existence, the silent measure between notes in the cosmic symphony. Without it, the music would have no pause, no depth. Scientists have attempted to recreate the cold of the cosmic void here on Earth. Inside ultra-high vacuum chambers, engineers remove almost every atom of air, reaching pressures lower than those in intergalactic space. In these chambers, they can measure temperatures of a few millikelvin above absolute zero. Yet even these perfect vacuums are warm compared with the void. The walls of the chamber still emit infrared light. The atoms still vibrate slightly, and gravity itself maintains a faint, unavoidable energy. To mimic true cosmic emptiness would require not just removing matter, but expanding space itself, a feat only the universe can perform. Perhaps the most poetic thing about the void's temperature is how it connects extremes. The hottest stars and the coldest regions of nothing both belong to the same continuum of cosmic evolution. The heat of creation spreads outward, thins and cools, until it becomes the chill of emptiness. What began as fire becomes silence. What began as motion becomes stillness. And yet within that stillness lies the memory of everything that ever burned. Every photon of the cosmic background once belonged to a universe filled with light. Each carries the faint echo of the original heat, stretched and softened by time. When you look into the black between stars, you are not seeing absence. You are seeing the universe's oldest story, the tale of fire becoming calm. If you could drift there, far from any galaxy, Surrounded only by the cold whisper of the background, you might feel something beyond sensation, a serenity that comes from perfect balance. Nothing moves too quickly, nothing pulls too strongly. The temperature of nothing is not merely cold, it is peace itself, the ultimate equilibrium, where every vibration has found its rhythm and every spark has learned to rest. It is the pause between the universe's heartbeats, the space where everything that once was continues to echo softly, endlessly, through the infinite night. Section 5. The Art of Making Nothing Colder. Laboratories that chase absolute zero. Imagine standing in a room so quiet that you can hear your own heartbeat and so still that the air itself has stopped moving. Now imagine trying to make that room colder, not by a few degrees, but by billions of tiny fractions of a degree. That is what scientists do when they chase absolute zero, the coldest possible temperature in the universe. It sounds impossible, and it is. In a literal sense, absolute zero, defined as negative 273.15 degrees Celsius, 0 Kelvin, is the point at which all classical motion of atoms ceases. It's the ultimate stillness, a state where energy vanishes and entropy reaches its minimum. Yet nature never quite allows us to get there. The closer we approach, the harder it becomes to remove the last flickers of motion, as if the universe itself guards this final secret. And still, we try, because in this extreme stillness, the laws of physics begin to change, or perhaps reveal themselves more clearly than anywhere else. The pursuit of absolute zero is not just a scientific experiment. It's a kind of cosmic meditation, a journey into the heart of silence itself. The first step in this journey begins with something familiar: cooling by contact. When two things touch, heat always flows from the warmer to the colder until balance is reached. That's how ice cools your drink, or how a metal rod feels cold when you pick it up. But this simple principle reaches its limit quickly. You can't use ice to reach negative 273 degrees Celsius. So physicists go beyond ice, beyond liquid nitrogen, beyond even the frigid temperatures of outer space. They start by using liquid helium, which boils at about negative 269 degrees Celsius. It is one of the coldest substances nature allows to exist as a liquid. In large tanks, the helium swirls like a ghostly mist, evaporating into a vapor that can freeze air on contact. Even at this point, atoms still jitter with measurable energy. To go further, scientists turn to ingenious techniques, methods that sound more like art than engineering. One of these is evaporative cooling. Just as sweat cools your skin when it evaporates, scientists can cool trapped gases of atoms by letting the fastest, most energetic ones escape. The remaining atoms share less energy between them, so the entire group becomes colder. This process can bring temperatures down to billionths of a degree above absolute zero. Another is laser cooling, perhaps the most poetic of all scientific techniques. It uses beams of light, the very essence of energy, to slow atoms almost to a stop. Here's how it works. When a photon of light hits an atom, it pushes it slightly, transferring momentum. By tuning lasers to a frequency just below an atom's natural absorption line, physicists can make the atoms absorb photons mostly when they move toward the light source. Each collision slows them, like invisible hands gently catching drifting dust. The result is astonishing. Clouds of atoms, so slow and cold that their movement becomes more like waves than particles. At this scale, physics enters the quantum realm. Inside these ultra-cold laboratories, strange and beautiful phenomena emerge. At temperatures near absolute zero, matter begins to lose its individuality. Atoms synchronize their quantum states, merging into one shared existence called a Bose-Einstein condensate, BEC. In a BEC, millions of atoms behave as if they were a single entity, one vast quantum wave. You can think of it as the opposite of heat. In hot gases, atoms rush and collide chaotically. In a BEC, they move in serene unison, their boundaries dissolving into harmony. To watch a BEC form is to witness the universe revealing its most delicate side. In a chamber smaller than your hand, under lasers shining like pastel rainbows, matter sheds its ordinary rules and becomes pure geometry. Patterns of light and interference, ripples of probability suspended in near stillness. At these temperatures, scientists can simulate the behavior of black holes, explore new forms of magnetism, and even mimic the physics of the early universe. In some sense, by making matter unimaginably cold, we glimpse how everything began and how it might end. You might imagine such experiments happening deep underground or on remote mountain peaks. But some of the most advanced cold atom labs are aboard the International Space Station. Up there, far from gravity's pull, NASA's Cold Atom Lab cools atoms to less than a billionth of a degree above absolute zero, colder than the depths of intergalactic space. Why space? Because in zero gravity, atoms can hover for long periods without falling or colliding with their containers. That extra stillness allows researchers to observe their quantum behavior for several seconds instead of fractions of a millisecond. The result? Clearer, slower, deeper glimpses into the world of pure physics. It's almost poetic that the coldest known place in the universe is not a distant nebula or a frozen moon, but a small metallic box, quietly humming aboard a space station orbiting Earth. There's something profoundly human about this pursuit. We live in a universe born from fire, from a big bang of unimaginable heat, and yet our curiosity draws us toward the opposite extreme, to freeze that fire, to still its motion, to find the quiet beneath the chaos. Every time we cool matter closer to absolute zero, we learn not just about atoms, but about limits, about how far stillness can go before it ceases to exist. We learn that even when everything seems motionless, there is still a whisper of life in the form of quantum energy. Nothing, it seems, can ever be perfectly silent. Even the vacuum vibrates with zero-point motion. Even light, when stretched to infinity, never fully stops. The deeper lesson, perhaps, is that stillness and motion are not opposites, but companions. To cool something down, you must first let it release its energy. To reach equilibrium, opposites must balance. This principle governs everything, from the way stars shine to the way atoms breathe. So, When scientists trap a handful of atoms and coax them toward absolute zero, they are not just doing physics. They are enacting a ritual of balance, mirroring the same cosmic dance that unfolds across galaxies. Every whisper of cold in their vacuum chamber echoes the silence between stars. Every flicker of laser light echoes the fading radiation of the early universe. And when they finally reach that near-perfect stillness, billionths of a degree above nothing, they stand at the edge of understanding, staring into the soft heartbeat of creation itself. The quest for absolute zero is not really about coldness. It's about finding clarity, a state where noise fades, where motion slows, and where the underlying structure of reality becomes visible. It is, in essence, a search for the universe's quiet truth. Section 6. The coldest places in the universe. Cosmic laboratories beyond Earth. If the universe could exhale, its breath would be frost. Everywhere, beyond the warmth of stars, lies an ocean of cold so deep, so silent, that even time seems to drift more slowly there. Yet scattered across this cosmic sea, there are places even colder than the ordinary void, natural laboratories sculpted by physics itself into realms of near-perfect stillness. To explore them is to walk through the chill corridors of creation, where the universe hides its softest whispers. When we think of cold, we often imagine frozen moons, icy comets, or the shadows of distant planets. And indeed, those are frigid worlds, places where temperatures plunge hundreds of degrees below zero. On Pluto, sunlight is so weak that the dwarf planet's surface stays around minus 230 degrees Celsius. Its mountains of frozen nitrogen and plains of methane ice glitter beneath a dim, faraway sun. Beyond Pluto, in the Kuiper Belt, countless other objects drift through darkness, their frozen surfaces barely touched by starlight. But even there, space is warmer than true cosmic emptiness. Those distant worlds, though frigid, still absorb faint sunlight and occasionally the warmth of radioactive decay inside their rocky cores. To find the coldest places of all, we must travel beyond worlds, into the vastness between them. One of the most remarkable natural freezers in the universe lies 5,000 light-years away, in the constellation Centaurus. It's called the Boomerang Nebula, and it holds the title of the coldest known natural place in existence. This ghostly cloud, about a light-year across, is a dying star's last breath. In its final moments, the star expelled its outer layers into space, forming a shell of gas expanding at enormous speed. As the gas spread outward, it cooled, not just by losing heat, but through the process of adiabatic expansion. In simple terms, when gas expands rapidly, its energy spreads thinner, and its temperature drops. In the Boomerang Nebula, this effect is so extreme that its temperature has fallen to about 1 Kelvin. That's minus 272 degrees Celsius, just 1 degree above absolute zero. Even the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe at 2.7 K, is warmer than this nebula. The Boomerang Nebula has managed, through natural processes alone, to become colder than the very fabric of space itself. If you could drift inside it, surrounded by its soft blue glow, you'd find yourself in an environment where motion nearly stops, where even atoms struggle to vibrate. It is, in a sense, a natural version of the cryogenic laboratories we build on Earth, except on a scale of light years. But the Boomerang Nebula is not alone in its quiet cold. Throughout the cosmos, there are pockets of intense stillness, regions so shaded, so hidden, that warmth cannot reach them. In the shadows of craters on the moon, for example, there are places that have not seen sunlight in billions of years. At the lunar South Pole, craters like Shackleton and Hermite hold temperatures as low as -250 degrees Celsius, making them colder than Pluto. NASA's Lunar Reconnaissance Orbiter has mapped these dark basins, revealing sheets of water ice preserved in their eternal night. On Mercury, too, the planet closest to the Sun, polar craters remain in permanent shadow, with regions that dip below -170 degrees Celsius. The paradox is striking. The world nearest the Sun also holds some of the coldest places in the solar system. Venture farther out, and cold becomes a constant companion. On Triton, Neptune's largest moon, the surface temperature hovers near -235 degrees Celsius, colder than liquid nitrogen. There, frozen nitrogen geysers erupt into thin plumes, then fall back as delicate frost. The entire moon gleams with a pale, bluish light, like an ancient gemstone locked in ice. And beyond Triton lies a kingdom of frost, the Kuiper Belt and the Oort cloud, where trillions of comets drift in near absolute darkness. These frozen travelers contain the primordial ingredients of the solar system: water, methane, ammonia, locked in slumber since the dawn of time. They orbit silently, awaiting the rare moment when one is nudged inward and glimpses the warmth of the sun once more. Each comet that wakes is a brief reminder of how the universe alternates between two states: blazing birth and frozen rest. Yet the deepest cold does not belong to solid surfaces or frozen gases. It belongs to empty space itself. Between galaxies, in the great cosmic voids, temperatures rest just above 2.7 Kelvin, the baseline set by the cosmic microwave background. These are places where starlight never travels, where no galaxy shines. The Boots Void, one of the largest known, spans nearly 300 million light-years across. Inside it, there are only a few dozen galaxies, scattered like lonely islands on a black ocean. The space between them is almost unimaginably empty and cold beyond comprehension. It is in these voids that the universe's ultimate destiny can be glimpsed. As time stretches onward, galaxies will drift apart, stars will burn out, and all radiation will fade. The cosmos will approach a state of uniform chill, a heat death where temperature differences no longer exist, and the cold of the void becomes the universe's final resting temperature. In that far future, every corner of existence will resemble the Boomerang Nebula, quiet, motionless, beautifully cold. But for now, these frozen realms remind us that even in stillness, the universe is alive with structure. The cold does not mean deadness. It means potential, preservation, pause. In the depths of these icy regions, molecules remain intact for billions of years, waiting for the warmth of a star to awaken them. Comets that sleep in the outer darkness may someday deliver water and organic molecules to new worlds, seeding life's beginning once again. In this sense, cold is not an end, but a waiting place, a cradle for future heat. The coldest places in the universe are not merely curiosities. They are mirrors reflecting nature's patience. They show us that the cosmos values stillness as much as motion. Just as stars need darkness to shine, warmth needs coldness to be meaningful. And so, from the Boomerang Nebula's frozen beauty to the moon's eternal shadows, we see the same truth repeated. The universe breathes in cycles, heating, cooling, expanding, resting. Each phase necessary, each beautiful in its own quiet way. If you could stand on the edge of one of these icy domains and look out into the infinite dark, you might feel something profoundly peaceful. The silence would not feel empty. It would feel full, full of waiting, full of potential, full of time. For in the coldest places in the cosmos, the universe is not gone. It is simply resting between heartbeats. Section 7. The slow music of frozen time. How cold changes the flow of the universe. Time has a rhythm. You can feel it in the ticking of a clock, in the pulse of your heart, in the cycles of day and night. But beyond our everyday experience, time itself has a subtler beat, one set by temperature, by the trembling of matter, by the energy that fills the world. When things are warm, they move quickly. Molecules dance, atoms vibrate, reactions unfold in bursts. In warmth, time feels alive, everything happening, everything changing. But as the temperature falls, movement slows. The vibrations grow weaker, reactions take longer, and time itself seems to stretch, becoming slower, deeper, quieter. At first, this is just chemistry. Cold slows molecules down. But in the vastness of the cosmos, where temperatures plunge to the edges of existence, the connection between cold and time becomes something profound, something almost mystical. Imagine standing in a laboratory where scientists cool atoms to billionths of a degree above absolute zero. Inside a small chamber of glass and light, a cloud of atoms hovers, nearly motionless. To the naked eye, it looks like nothing, a faint shimmer suspended in still air. But to sensitive instruments, those atoms are moving in slow motion, their vibrations reduced to almost nothing. At such temperatures, chemical reactions can take minutes, hours, or even years to occur. Processes that happen instantly at room temperature seem to freeze in time. You could say that cold makes time move differently, not because time itself slows, but because the universe's capacity to change fades away. At the limit of absolute zero, no movement remains to measure time by. The clock of matter stops ticking. Einstein showed us that time and motion are inseparable. In the theory of relativity, the faster an object moves through space, the slower time passes for it. But in a poetic symmetry, the slower matter moves. The closer it approaches absolute stillness, the less meaningful the passage of time becomes. Temperature, in a way, is a measure of how much the universe remembers the flow of time. Every vibration, every exchange of heat, every flicker of motion is an echo of the cosmic clock. When temperature falls towards zero, that echo fades. In the deepest cold, a kind of temporal silence begins. You can see this relationship between cold and time even in the natural world. Deep beneath the Arctic permafrost, seeds buried for tens of thousands of years remain viable, their biological clocks nearly paused. In the cold vacuum of space, spacecraft components can drift for centuries without corrosion or decay. Cold preserves. It slows entropy, the measure of disorder that drives time's arrow forward. When you freeze something, you hold it at the edge of change. It neither decays nor grows. It waits. The same principle applies on cosmic scales. In the cold clouds of interstellar space, molecules that would normally react in seconds on Earth can endure for millions of years. The frozen nebulae and cometary ices of the outer solar system are archives of history, keeping pristine samples of matter from the dawn of creation. In the cosmic cold, time is not erased, it is stretched. To grasp this fully, imagine what happens in the Boomerang Nebula, the coldest known place in nature. There, at about 1 Kelvin, atoms move so slowly that their interactions almost cease. If you could watch them, if your eyes could somehow see over a span of thousands of years, you'd find that change happens at a glacial pace. A molecule might rotate once in an hour. A single collision could take a century. In that near stillness, time would feel infinite. You would sense no progression, no before or after, only an endless, motionless now. This is the secret music of frozen time, a melody stretched beyond hearing, where the notes are years apart. At such extremes, even light behaves differently. Light is the purest clock in the universe. It defines time through its constant speed. Yet, in ultra-cold conditions, when light interacts with matter that's nearly frozen, it can be slowed, even stopped momentarily. In 1999, scientists at Harvard used a cloud of supercooled atoms to slow a pulse of light to just 17 meters per second, slower than a bicycle. Later, they managed to freeze light entirely, storing it in a quantum state for a few fractions of a second before releasing it again. To freeze light is, in a sense, to freeze time's heartbeat. It is a reminder that coldness doesn't only affect matter, it touches the very rhythm by which reality unfolds. Some physicists believe that the universe itself might be slowly cooling time as it expands. As the cosmos stretches, radiation loses energy and the overall temperature of space drops. One day, in a distant, unimaginable future, the universe may reach a point where every process slows to near zero. Stars will fade, black holes will evaporate, and all remaining atoms will rest in dark equilibrium. In that far future, time will lose its meaning, not because it has ended, but because nothing will happen anymore. The cosmic song will have played its last note, leaving only the long, gentle echo of silence. But cold is not only an end, it is also a beginning. Just as heat allows creation through fusion and movement, cold allows preservation and structure. Without it, stars would burn too fast, planets would never form, and life's fragile molecules would fall apart. In the spaces between warmth, the universe finds balance. The rhythm of existence depends on contrast, motion and stillness, fire and frost, time and its suspension. When you stand outside on a winter night and feel the cold air against your skin, you're touching that balance directly. The chill you feel is not emptiness, it's the whisper of a universe keeping time, slowing just enough to let you feel its pulse. To think of cold this way is to see it not as an absence, but as a tempo, a slower measure in the symphony of being. Heat is a quick movement, a bright, loud rhythm. Cold is the pause, the held note, the silence between breaths. Both are part of the same cosmic composition. And somewhere, in the deepest stillness of interstellar space, that music continues, faint, vast, and eternal. Atoms drift like notes suspended on an invisible staff. The tempo slows and slows and slows, until one day, perhaps, the music ceases altogether, and the universe rests in the final measure, a long, perfect, everlasting pause. Section 8. Frozen light. The secrets of the coldest photons. Light in its purest form is motion. Energy on the move, endlessly restless. It crosses the cosmos without slowing, weaving its invisible threads through galaxies and time itself. Light is warmth, life, memory, and witness. But what happens when light itself begins to grow cold? Can something that never stops moving ever lose its heat? The answer lies in one of the universe's most haunting phenomena, frozen light. The light so stretched, softened, and thinned by time that it has become the faintest whisper of its former brilliance. In the beginning, light was everything. When the universe was born in the fire of the Big Bang, it was a storm of energy. The first few minutes of existence were filled with radiation so intense that atoms could not form. Only a glowing plasma of pure light and matter intertwined. But as the universe expanded, that brilliance began to cool. Photons, the particles of light, stretched as space itself stretched, losing energy as their wavelengths grew longer. From gamma rays, they softened into X-rays, then into visible light, then into radio waves. Today, what remains of that primordial glow is the cosmic microwave background, CMB, a bath of ancient light that fills every corner of the universe. Its temperature is just 2.725 Kelvin above absolute zero, making it the coldest light we can measure. This radiation is the afterglow of creation, light that has been traveling for 13.8 billion years, stretched by time, cooled by distance, and quieted into a faint, uniform hum. If you could see the cosmic microwave background with your eyes, the universe would no longer look black. It would shimmer faintly in every direction with a ghostly orange-red glow, dim but omnipresent, the eternal sunset of the cosmos. Every photon in that glow has been on a journey since the universe was 380,000 years old, when atoms first formed and the fog of plasma lifted. Those photons carry the imprint of the cosmos's earliest structure, tiny fluctuations that later grew into galaxies and stars. Even now, they pass through your body by the trillions each second, invisible and harmless, like time itself brushing against your skin. Light, as it cools, becomes time's diary. It remembers every expansion, every shift, every gravitational nudge along its path. When astronomers look at distant galaxies, they are looking not at what they are, but what they were: light delayed, stretched, aged. The farther we look, the older and colder the light becomes. Some of the most distant light ever detected from the earliest galaxies has been stretched so much that its original visible glow now arrives as faint microwaves. These photons have been traveling for nearly the entire history of the universe. Each is an echo, a frozen ember of an ancient fire that once illuminated the newborn cosmos. In the coldest reaches of space, light behaves differently. Between galaxies, where the vacuum stretches for millions of light years, photons drift almost unimpeded, their energy diluted by emptiness. Some interact with stray particles, losing even more energy. Others are bent and stretched by the pull of gravity, a process called gravitational redshift, making them older, softer, colder still. In this way, light becomes the memory of motion, its once fiery essence transformed into stillness through the passage of time. And yet, even in its coldest form, light never truly dies. It continues forever, cooling as the universe expands, its wavelength stretching toward infinity. In the far future, when the cosmos has aged beyond stars and galaxies, the last remaining light will be low-energy radio waves, so faint that their presence will be almost theoretical, the final, lingering hum of creation. But light can freeze in another, more literal way, not just in space, but in laboratories on Earth. In 2001, scientists managed to do something once thought impossible. They stopped light completely, using a cloud of atoms cooled to near absolute zero. They trapped a pulse of laser light, storing it for a few milliseconds before letting it continue on its path. To do this, they used a quantum trick called electromagnetically induced transparency. The ultra-cold atoms acted like a mirror made of time itself, absorbing the light and holding its information as a quantum pattern. When the light was released, it continued as if nothing had happened, but during those milliseconds, it had been frozen. In that moment, light ceased to be motion. It became memory, energy held in stillness, like a breath suspended in glass. This experiment gave us a glimpse into something profound, that even light, the universe's fastest traveler, can be made to rest, and that time, for a brief moment, can be persuaded to pause. In space, however, the freezing of light happens not in milliseconds, but across billions of years. As the universe expands, wavelengths stretch endlessly, cooling the radiation field. The once blinding light of stars becomes infrared, then microwave, then radio, until it is indistinguishable from silence. In the far, far future, when the universe has aged beyond all measure, even the cosmic background will fade to invisibility. Its photons will be so stretched that their energy approaches zero. The cosmos will then be filled with frozen light, light that has traveled so long and so far that it has forgotten how to shine. This era, called the Dark Era, is the theoretical end of all radiance. Yet even then, light will not be truly gone. It will exist as pure wavelength, infinitely long, infinitely faint, still moving, still whispering, still remembering the fire that began it all. To speak of frozen light is to speak of time slowed to its ultimate limit. Every photon, no matter how old or cold, carries a piece of the universe's heartbeat, a rhythm that began at the dawn of everything. Light cannot die, only fade. It can lose energy, but never identity. It can stretch until it becomes silence, but even silence has form. Somewhere in the blackness between galaxies, there are photons that have traveled for nearly 14 billion years. They are so faint that they carry almost no energy, yet they are still moving, still alive in the most delicate sense imaginable. They are the ghosts of creation, forever wandering through the dark. If you were to drift among those photons, beyond stars, beyond time, you would see no brightness, no color, no form, but you would feel their presence, faint and eternal, brushing softly against the atoms of your body. In their silence, you would hear the memory of light, and in that memory, you would understand something deep and quiet, that even when everything cools, even when time itself slows to a whisper, the universe does not end. It simply becomes still enough to remember itself. Section 9. The universe's natural cryostats, how space keeps itself cold. When we look out into the night sky, we often think of space as vast and empty, a place where nothing happens. But this apparent emptiness hides a delicate balance. The cosmos is not simply cold because of absence. It is cold because of design, a quiet, natural mechanism that allows it to preserve its chill, like the greatest cryogenic chamber ever built. Space, in every sense, is the perfect freezer. To understand why the universe is cold, we must first understand what makes something warm. On Earth, warmth is motion, molecules vibrating, atoms colliding, energy flowing from one body to another. But in space, there are almost no atoms at all. A single cubic meter between the stars might contain only a handful of particles. Without matter to carry heat, there is nothing to stay warm. In space, temperature is not so much about the air or surroundings, but about radiation, the exchange of energy through light and invisible electromagnetic waves. Every object emits radiation based on its temperature. The hotter it is, the shorter the wavelength of its emitted light. Stars shine because they are billions of degrees hot. Planets glow faintly in infrared. But far from any stars, where there is no source of energy, the radiation field is almost empty, except for the faint afterglow of the Big Bang, the cosmic microwave background. That faint background, at just 2.7 Kelvin, is the floor of temperature for most of the universe. It is what fills the void, what defines cosmic cold. Imagine drifting in deep intergalactic space. No planets, no stars, just a slow, endless blackness. If you were to measure the temperature of your surroundings, you'd find it almost constant everywhere. 2.7 Kelvin. That's colder than any place on Earth, colder than liquid nitrogen, colder than nearly all known substances can exist in. You would be inside a natural cryostat, a region of space kept cold, not by design or engineering, but by the simple geometry of the universe's expansion. The cooling of the universe began with the Big Bang. At its birth, the cosmos was unimaginably hot, dense, and bright. Temperatures reached trillions of degrees, so high that matter and energy were inseparable. But as the universe expanded, that same energy was stretched thinner and thinner across increasing space. Expansion does not just make the universe larger, it drains energy. Every photon of light is stretched, its wavelength lengthened, and with that stretch comes a loss of temperature. This process, cosmic redshift, is why the universe has cooled from its original inferno to its current frigid calm. In a way, space cools itself simply by growing. It's as if, with every breath of expansion, it exhales warmth and keeps what remains at bay. The cosmic background radiation that fills space today is the remnant of a much hotter time. When the universe was just 380,000 years old, it was about 3,000 Kelvin, glowing with visible light, like the surface of a star. As expansion continued, that glow shifted into the microwave range, cooling by a factor of 1,000. Now, after nearly 14 billion years, it has settled into near-perfect uniformity. It acts like an invisible, all-encompassing bath of radiation that defines the cosmic temperature. Nothing in the natural universe can cool below it, unless shielded from it somehow. And yet, some regions do get colder. Inside dense molecular clouds, where dust and gas block out background radiation, temperatures can drop to as low as 1 Kelvin. These regions are like pockets of supercooled darkness, shadowed laboratories of nature where stars are born. How do they achieve such stillness? Because they are isolated. Their thick layers of dust absorb and scatter incoming light, allowing the inner regions to radiate their own faint heat away into the surrounding vacuum. Without any incoming energy, and with every bit of warmth escaping outward, they reach extreme lows. These star-forming clouds are the universe's natural deep freezers, places where the cosmos quietly stores the ingredients for creation in the coldest possible state. But perhaps the most fascinating aspect of the universe's cooling mechanism is that it is self-sustaining. Unlike a refrigerator, space does not require energy to stay cold. It becomes colder with time because the universe itself is doing the work, expanding, stretching, thinning out its own energy. And as it continues to expand, it will grow colder still. In the distant future, trillions upon trillions of years from now, the cosmic microwave background will no longer be microwave radiation at all. It will be stretched into radio waves so long that their wavelengths will span entire planets. The temperature of the universe will have dropped to a fraction of a Kelvin. This is the direction the cosmos is heading, toward the cosmic winter, known as heat death, a time when everything has cooled so completely that no usable energy remains. Even now, space is not entirely uniform in temperature. There are tiny variations, differences of a few millionths of a degree in the background radiation. These subtle ripples are the fingerprints of the early universe, the tiny seeds from which galaxies and stars eventually grew. Without them, the universe might have remained a perfectly smooth, frozen fog. No stars, no planets, no life. It was the slight unevenness in the cosmic cryostat that allowed heat to collect in some regions and disperse in others. Cold, therefore, is not merely an absence, but a sculptor, shaping where light and matter would one day ignite. If you think about it, this is one of the most poetic truths in science. The same forces that made the universe cold also made it possible for warmth to exist. Because only in a cold cosmos can stars stand out, only against a black, frigid background can their light shine. The universe's chill gives meaning to its warmth. It frames creation, contrast, and existence itself. And so, the cosmos remains its own perfect cryostat, a system without walls, without electricity, without design, yet perfectly efficient at preserving its icy stillness. Every galaxy, every star, every particle floats in that chill, surrounded by an eternal coolness that hums softly at 2.7 Kelvin. It is a universal silence, the equilibrium of everything that ever was. If you could listen to it, you might hear nothing, but feel everything. You would sense the delicate balance of a universe constantly cooling, constantly expanding, constantly whispering its slow retreat into the calm. The cosmos, after all, has always been moving toward stillness, and in that stillness lies its greatest secret, that cold is not emptiness, but peace. Section 10. When time freezes, the quantum stillness near absolute zero is a point hidden at the bottom of the temperature scale where warmth fades into silence and motion becomes a memory. This point, absolute zero, at negative 273.15 degrees Celsius or 0 Kelvin, is the coldest temperature allowed by the laws of physics. It is not merely a number. It is a border, a threshold where time itself seems to hesitate. At absolute zero, all motion that can stop has stopped. Atoms no longer vibrate. Molecules no longer twist or collide. Energy, which gives shape to existence, has retreated into the smallest, quietest possible form. And yet, even here, at the edge of nothing, something astonishing happens. Reality begins to glow with quantum light. When we cool matter, what we are really doing is slowing down motion. At room temperature, atoms move at hundreds of meters per second, colliding, vibrating, exchanging energy in chaotic patterns. As we cool them, their motion slows. At a few degrees above absolute zero, they move only centimeters per second. And at billionths of a degree above zero, their motion becomes so subtle, so perfectly coordinated, that the rules of quantum mechanics emerge into the visible world. It is here that ordinary matter, the kind that makes up everything we know, begins to behave like something entirely new. In 1995, physicists Eric Cornell and Carl Wieman achieved what had once been only a dream. Using a combination of magnetic fields and laser cooling, they slowed a cloud of rubidium atoms to just 170 nanokelvin, that is, 170 billionths of a degree above absolute zero. At this unfathomable cold, something miraculous occurred. The atoms stopped behaving like individual particles. They blurred together, overlapping, forming a single quantum entity, one vast, delicate wave. This was the creation of the Bose-Einstein condensate, a state of matter so strange it behaves more like light than like solid, liquid, or gas. Every atom within it shares the same quantum state. They move together, oscillate together, and in a sense, think together. It was as if, by cooling matter enough, scientists had peeled back the ordinary world and revealed the quiet, unified heartbeat beneath it. At temperatures near absolute zero, time seems to lose its rhythm. The motion that defines time, the constant vibration and exchange of energy, slows until it almost stops. To an atom in such a state, The concept of before and after nearly disappears. Every possible position, every possible energy level blends into one timeless pattern. In this frozen realm, the universe reveals its most subtle truths, that everything is connected, and that the boundaries we perceive between one atom and another are, at the deepest level, illusions of warmth and motion. When all that agitation is gone, what remains is pure coherence, matter as a single, united field of existence. Time itself is not a thing. It is an experience of change. We know time because things move, because atoms oscillate, because light travels and hearts beat. At absolute zero, the stage for these rhythms collapses. Without motion, without energy exchange, change halts. And so in a very real sense, time freezes. Physicists have even speculated that a system cooled to true absolute zero would be perfectly static, unchanging, and eternal. But nature does not quite allow that perfection. Thanks to quantum uncertainty, even the coldest atom retains a whisper of motion, a faint vibration called zero-point energy. It is the universe's way of saying, I cannot stop completely. No matter how cold you make something, there is always a remnant of life within it, a flicker of energy that can never be removed. This tiny vibration is not a flaw, but a fundamental truth. It is the hum of existence itself, the signature of a cosmos that never truly sleeps. When scientists cool matter toward absolute zero, they witness effects that defy intuition. Liquids like helium become superfluids, able to flow without friction, climbing walls and looping endlessly without losing energy. Electrons in metals form superconductors, moving through wires with perfect efficiency, unimpeded by resistance. In both cases, it's as if the particles have learned to cooperate perfectly, moving not as individuals, but as one. At such low temperatures, the line between solid and liquid, between particle and wave, between motion and stillness, begins to dissolve. Matter becomes more like thought, abstract, smooth, and collective. In space, far from human laboratories, such cold may exist naturally in small, temporary pockets, in the shadows of interstellar dust clouds, in the faint gases that drift between galaxies. Atoms may reach just a few degrees above absolute zero, but they can never reach zero itself. Even the deepest cosmic night cannot quiet the faint hum of quantum energy that pervades everything. This universal whisper, that last remaining vibration, is what connects the infinitely cold to the infinitely hot. It is the thread that runs through every atom, every photon, every moment of time. Near absolute zero, the boundaries between science and philosophy blur. Physicists studying Bose-Einstein condensates often describe them with words that sound more like poetry than mathematics. They speak of frozen light, quantum silence, and matter in thought. It's as though, at the very bottom of the temperature scale, nature becomes contemplative. All the noise, the chaos, the collisions, all the frantic movement that makes up the visible world fades into a serene unity. At absolute zero, reality becomes simple. Everything that can be known about matter is written into a single, quiet wave. To look at it is to see the universe in its most peaceful state, a portrait of stillness painted with quantum ink. The pursuit of absolute zero is not just a scientific challenge. It's a philosophical journey, a search for the still point of creation, the calm beneath all motion. When humans first built fires, they learned to control heat. When they built refrigerators, they learned to preserve. And when they began to chase absolute zero, they began to understand the structure of existence itself. Because to make something colder is to slow its story, to quiet the song of atoms until you can hear the silence behind it. And in that silence, there is a message that even when motion stops, connection remains. That underneath all chaos and heat, there is a still, unified field of being, patient, perfect, and eternal. If you could stand beside a Bose-Einstein condensate and somehow perceive its quantum unity, you might feel as though time had slowed around you. There would be no sensation of warmth, no vibration, no change, only stillness, a kind of frozen eternity, humming softly at the edge of being. And yet, within that stillness, the universe continues to breathe, gently, invisibly, with the faintest pulse of zero-point energy. Even in perfect cold, existence refuses to vanish. It simply becomes quiet enough for us to feel how infinite it truly is. Section 11. The Cosmic Freezer, How Black Holes and Expansion Shape the Universe's Ultimate Cold. The universe is cooling. Every second, with every heartbeat of expansion, it grows colder still. The warmth of the stars, the glow of galaxies, the faint shimmer of the cosmic background, all of it is slowly fading into darkness. If you listen closely, not with your ears, but with your imagination, you can almost hear it, the sound of everything exhaling. The cosmos is relaxing, stretching, releasing its heat into the infinite. It is, in every sense, becoming its own perfect freezer. But this process is not random. It is shaped by gravity, by the mysterious pull of black holes, and by the silent acceleration of dark energy, two of the most powerful and enigmatic forces in existence. Together, they form the machinery of the universe's long, slow cooling. In the beginning, the universe was heat. For hundreds of thousands of years after the Big Bang, everything glowed, a brilliant sea of light and plasma so hot that atoms could not exist. Over time, expansion stretched this fire into calm. The universe grew, light cooled, matter formed. Stars ignited, galaxies spun, and for billions of years, warmth returned. The warmth of starlight, of fusion, of cosmic life. But that warmth is temporary. Stars are finite furnaces. They consume their fuel, and when that fuel is gone, they die, some quietly, some with a final flare. And when they die, they leave behind darkness, the burnt-out cores of white dwarfs, neutron stars, and, most mysterious of all, black holes. It is these remnants that now govern the cooling of the cosmos. A black hole is not a thing in the usual sense. It is a region of space-time so deeply curved that nothing, not even light, can escape its gravity. To the outside observer, it appears as a sphere of perfect blackness, an invisible freezer where heat itself seems to vanish. Yet, paradoxically, black holes are not entirely cold. In 1974, physicist Stephen Hawking discovered something astonishing. Black holes radiate energy. Through quantum effects at their event horizons, the invisible boundaries where gravity and quantum mechanics collide. They emit a faint glow of thermal radiation. This Hawking radiation is unimaginably weak, but it means that black holes, too, have a temperature. The smaller the black hole, the hotter it glows. The larger it is, the colder it becomes. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvin, far colder than the background radiation that fills the universe. And supermassive black holes, like the one at the center of our galaxy, are colder still, fractions of a nanokelvin above absolute zero. They are in many ways the coldest natural entities we know of. Yet even these frozen giants play a role in the universe's gradual loss of heat. Over unimaginable spans of time, they will slowly evaporate. Their faint Hawking radiation will bleed energy back into the cosmos, until, after perhaps 10 to the power of 100 years, they too will vanish. In that far future, there will be no more stars, no more galaxies, only scattered atoms, fading radiation, and black holes slowly dissolving into emptiness. The universe will then be colder than it has ever been, a near absolute stillness, where even the speed of decay feels like a whisper. But black holes are not the only agents of this cosmic freezing. There is something else, even more profound, that ensures the universe's continual cooling: the expansion of space itself. For reasons science still does not fully understand, the universe's expansion is accelerating. This acceleration is driven by dark energy, an invisible pressure that pushes galaxies apart faster and faster as time goes on. As space expands, it stretches light, drains energy, and isolates galaxies from one another. Eventually, distant galaxies will drift so far away that their light will never reach us again. The night sky will empty. In that era, the only warmth remaining will come from the slow decay of matter, the faint radiation of dying particles, and the last embers of black holes. Everywhere else, there will be silence colder than thought. It is strange to imagine a universe ruled by cold. We tend to think of life, motion, and creation as products of heat, and indeed, they are. But cold, too, is a kind of order, a quiet arrangement of things when chaos has burned itself out. In the far future, when the last black hole finally evaporates, the cosmos will be an ocean of low-energy photons, light so stretched it has almost no frequency at all. Temperature will approach absolute zero. Time will lose meaning because nothing will change. This is the final equilibrium physicists call heat death, not an explosion, not an ending, but a long exhale into stillness. The universe will not collapse or vanish. It will simply grow quiet, perfectly, infinitely, beautifully quiet. If we could look into that distant future, not with eyes, but with imagination, we would see a cosmos without stars, without light, without contrast. Galaxies will have evaporated. Matter will have decayed. The only remaining energy will be the faint, ghostly glow of the last photons fading into infinity. Yet even then, some mysteries will remain. Even at near absolute zero, quantum uncertainty will persist. There will still be ripples in the field of existence, faint vibrations that can never quite disappear. The universe, in its final stillness, will still remember that it once burned. In this sense, the coldest era of the universe will not be its death, but its rest, All the motion, all the noise, all the struggle of gravity and heat will have run its course. What remains will be pure equilibrium, a kind of cosmic peace. Perhaps at that moment, the universe will be closer to perfection than ever before. No imbalance, no motion, no pain, only silence. And maybe that silence is not an ending at all, but a beginning. The universe's way of preparing for another breath, another dawn, another cycle we cannot yet imagine. Because cold, when seen this way, is not emptiness. It is clarity. It is the slow rhythm of eternity unfolding. Black holes, dark energy, and the stretching of space are not destroyers. They are sculptors of calm, patiently shaping the universe toward its ultimate stillness. And when that stillness finally arrives, when the last photon drifts across an infinite frozen sea, the cosmos will have completed its story, from fire to frost, from noise to silence, a grand exhalation of creation. And then, the quiet peace that follows. Section 12, The Sound of Nothing, How Cold Shapes Silence Across the Universe. If warmth is motion, then sound is its song. Every note, every whisper, every vibration that travels through air or water or rock is the echo of energy in motion. To hear something is to feel the dance of atoms, and to lose sound entirely is to enter a deeper quiet than any silence we know on Earth. In space, silence is not simply the absence of noise. It is the absence of the possibility of noise. And at the heart of this silence lies cold. On our planet, sound is everywhere. The hum of life fills the air, the rustle of leaves, the distant thunder, the rhythm of a heartbeat. Sound is a tapestry of motion, of molecules colliding and passing along vibrations. But sound cannot travel through a vacuum. It needs a medium, something to push and pull, to carry its waves. Without atoms to move, vibration stops. In the deep void between stars, there are only a few stray particles in every cubic meter, far too few to carry a whisper. Out there, silence isn't a lack of sound you can't hear, it's a lack of sound itself. This is not silence as we experience it in a quiet room or a snowy forest. It is absolute silence, a silence that exists not because something has stopped, but because there is nothing to begin. Yet even in this cosmic stillness, there are faint echoes, not of sound, but of motion. Cold does not merely stop vibration, it transforms it. As temperatures drop, atoms slow, their collisions lessen, and their vibrations weaken. When the cold deepens toward absolute zero, those vibrations fade into quantum whispers, faint oscillations that exist only because they cannot be removed entirely. This residual motion is called zero-point energy, and it ensures that even the coldest atom still hums with an inaudible, eternal note. It is the universe's quiet heartbeat, the song beneath silence. On Earth, we can approach this same kind of stillness inside cryogenic chambers and ultra-cold laboratories. When scientists cool matter to near absolute zero, sound waves slow dramatically. In supercooled gases, they travel thousands of times slower than they would through air, as if even the air's ability to carry a whisper has frozen. At these temperatures, sound itself becomes a rare, delicate phenomenon, no longer a physical pressure wave, but a quantum ripple, like the faint shimmer of a thought. And yet, In the silence of the ultra-cold, new kinds of sound appear, sounds that have never existed in the ordinary world. Inside Bose-Einstein condensates, where atoms move in perfect unity, vibrations become coherent across the entire cloud. A single disturbance can ripple through millions of atoms like a symphony of light. A quantum sound known as a phonon. Phonons are the sound of the frozen universe. They are not mechanical vibrations, but patterns of quantum movement. Soft, silent harmonies played on the strings of reality itself. If space is silent, then where does cosmic sound live? In the early universe, before matter cooled, there was sound everywhere. The plasma of the newborn cosmos, a thick soup of ions and light, carried pressure waves across its vastness. These waves rippled through the hot gas like the ringing of a bell, creating compressions and rarefactions that later became the seeds of galaxies. The cosmic microwave background we see today still carries traces of those primordial vibrations, frozen into light as faint temperature ripples. It is, in a very real sense, the echo of the universe's first sound. The cosmos once sang, and now it listens to its own silence. Silence, in the cosmic sense, is not a void. It is a texture, soft, stable, infinite. In the darkness between galaxies, you can imagine that silence as a tangible thing, smooth, dense, and utterly still. Every object, every atom, radiates faintly into that silence. Even the quietest, coldest dust cloud hums in infrared light, a kind of luminous whisper. And yet, compared to the wild music of the early universe, this modern cosmos is nearly motionless. It has settled into a long, peaceful rest, a silence so vast it feels alive. Still, the universe is not perfectly mute. Gravity creates its own form of sound, gravitational waves, ripples in space-time itself. When black holes collide or stars collapse, they send tremors through the very fabric of existence. These waves are not carried by air or matter. They are distortions of space itself. They move without a medium, and they travel at the speed of light. We cannot hear them with our ears, but instruments like LIGO and Virgo can detect their delicate symphony, the low, bass-like rumble of space-time breathing. If we could translate these gravitational waves into sound, they would be deep, soft notes, tones that last for seconds or even years. The song of merging black holes, the whisper of the cosmos remembering its own shape. But even these sounds fade as the universe grows colder. As energy thins, as collisions become rare, the great cosmic orchestra quiets one instrument at a time. Cold and silence are, in the end, the same language spoken at different scales. Both mark the slowing of energy, the retreat of motion. Both are the spaces between notes, the pauses that give rhythm to existence. If the universe began as a fiery explosion, a great cosmic chord, then it is ending as a single infinite rest, a final breath drawn out over trillions of years. And yet, silence has beauty. It is not empty. It is complete. The absence of sound allows what remains to be heard. The heartbeat of stars, the hum of atoms, the whispers of memory. Perhaps this is why so many people feel peace when they imagine the void of space. It is not death that calls from that darkness, but stillness. It is the serenity of a universe that has played its song and now rests in its final note. The cold of space is not the enemy of sound, but its teacher. It shows us that all things that sing must one day quiet, and that quiet is not the end of music, but its purpose. Because in every silence there remains an echo, and in every frozen atom there remains a vibration that will never stop. The sound of nothing is not nothing at all. It is the sound of everything at peace. Section 13. Frozen Time. When stillness touches eternity. Time and temperature are more connected than they seem. Both measure change. Both describe motion, and both slow when motion fades. At the heart of every clock, mechanical, atomic, or cosmic, there is motion. A pendulum swings. An atom vibrates. A particle oscillates between energy states. That rhythm, that heartbeat of movement, is what we call time. So what happens when the universe grows cold? When motion stops? When vibration, that faint trembling of being, slows toward stillness? It is then that we begin to glimpse a strange truth. Cold bends time. In the laboratories of Earth, where scientists cool atoms to within billionths of a degree above absolute zero, this effect becomes visible. The atoms move so slowly that their internal transitions, the oscillations that define an atomic second, stretch. When compared to warmer clocks, they tick just a little more gently. This isn't magic, it's physics. Energy and time are two sides of the same coin, bound by the laws of quantum mechanics. When energy fades, the rhythm of time softens. The universe becomes quieter, not only in sound, but in pace. If you could drift through a region of space colder than any star's shadow, time would seem different there. Your heartbeat might still pulse at the same pace, but the atoms of your body would move slower. The energy between them thinned almost to silence. Even light, stretched by the expansion of the cosmos, would crawl in long red waves, tired and dim. To an outside observer, you would appear nearly frozen. To yourself, everything would feel still. It is as if, near absolute zero, existence itself inhales and holds its breath. Physicists call this a kind of time dilation through energy loss, not the relativistic stretching caused by speed or gravity, but a gentler, subtler slowing, the quiet of energy becoming rest. Where there is no heat, there is no hurry, and the colder the system becomes, the closer it approaches timelessness. Absolute zero is not just the absence of temperature. It is the boundary where the arrow of time itself falters, because time as we experience it is driven by change, entropy, disorder, motion. But at absolute zero, there is no change. Entropy stops increasing. Everything becomes perfectly still. This does not mean time ends. It means time has nothing left to measure. A frozen second is indistinguishable from eternity. The same principle exists in our perception. When we are still, when our surroundings are quiet and the air is cold, time seems to stretch. Moments expand. Our awareness deepens. This is the human echo of the cosmic freeze. In a way, the cold teaches us what time really is. It reminds us that warmth is movement, that life is vibration, And that stillness is the quiet underside of time's melody. The cold does not destroy time, it reveals its edges. It shows that the rhythm of the universe can slow almost to nothing, and yet something remains. If one day, far in the future, the universe continues to expand and cool, it will approach a state called heat death, a cosmic stillness where all energy is evenly spread, where no motion or life remains. That will be the ultimate winter, not a night, not a void, but an eternal pause. And yet, even then, quantum physics tells us there will still be a whisper, that faint zero-point hum, the eternal restlessness that can never be erased, a spark of being that refuses to fade. It means that even in perfect stillness, existence will continue to hum. It means that even when time seems to stop, the universe still breathes, the quiet heart of the universe. When we speak of cold, we speak of endings, of stillness, silence, sleep. But there is a hidden beauty in it, because cold does not mean death, it means peace. The coldest places in the cosmos are not graves, they are mirrors, showing us what lies beneath motion, beneath sound, beneath the bright heat of being. They are places where existence rests, where the wild song of the universe pauses between notes. In those moments of near absolute stillness, in the faint hum of cosmic microwave light, in the frozen breath of interstellar clouds, in the soft glow of supercooled atoms, we glimpse the foundation of everything. The universe, for all its noise and fire, was born from calm, and to that calm it will one day return. Perhaps that is not an ending, but a homecoming. Because silence is not the opposite of creation, it is its source. When heat fades and motion stills, what remains is pure existence, unshaken, unhurried, eternal. That is the true meaning of absolute zero. Not death, but perfect rest.